In today's video, we're going to look at the SPSS Mixed model. This is just to figure out which buttons we push and maybe a little bit about what the output shows. Future videos will talk about effect size, p-values, and confidence intervals. In this example, we're going to do a one-way ANOVA with the longitudinal data, the vision data that we've used before. We've cut down the variables. The ID is the subject. The last refractive status is what refractive state the person was in at the end of the study. 0 extreme myopes, 1 myope, and so forth. We're going to be particularly interested in just looking at myopes. And so we're going to use a variable called init years, which means the relative time from initial diagnosis. So a -4 will be 4 years prior to the initial diagnosis of myopia. A +2 will be 2 years after the year of initial diagnosis. We're interested in 3 dependent variables: the spherical equivalent, the peripheral periphery's spherical equivalent, the relative peripheral refraction. And relative peripheral refraction is peripheral spherical equivalence minus spherical equivalence. So we're going to take a look at descriptive and see how many people we have. We have init years here. We're going to see that I've already analyze, data, select cases, all cases, okay. Analyze descriptives, frequencies, init years, and we see that we have data that goes from -6 down to +5. But we're pretty thin in the -6 and -5 and the +4 and the +5. So we're going to restrict our data range to -4 to +3 years. We do that with data, select cases, if a condition applies, and in this case it's if the last refractive status equals 1, which is the code for myope, and init years is greater than -5, which means -4 and above, and init years is less than 4, which means we don't take anything above 3 years. And that's going to leave us with a data set of those numbers. And it's going to look like this. Now, for example, here's a person that's hyperope, has all these slashes, a myope. It goes from -4 to +2. One thing about this data set is it is not complete on everybody. Here is another myope that goes from -2, doesn't do -3 or 4, and goes to +3. They also have a 4th year that we delete. Okay, we want to look at the one-way ANOVA with repeated measures, and that's with init years. So we go to a mixed model linear. ID is the subject number, so it's within subjects. It's repeated measures. So we have to identify what it's within, and so we move the ID over there. Init years is what's repeated. And the unique thing about mixed model and maximum likelihood estimated analysis of variance is that you can choose the covariance type that you're considering. Compound symmetry is what we're going to do. And that says that the variables are correlated, but they're all correlated the same with each other. A possible alternative would be autoregressive, which says that variables or years closer to each other are more correlated than years far apart. Turns out in this case compound symmetry was the best fit, so we're going to use that. Our dependent variable is spherical equivalent. We have our factor is init years. We have to put in the model, which in this case very simple, it's just init years. We want to look at the statistics, in this case mostly for illustration purposes, so it's going to estimate the parameters for the fixed effects. And we want to calculate the means of the init years. And we're going to compare the main effects, that is, in this case, we're going to do all the paired comparisons with init years. We're going to use a method called least significant difference. And it doesn't say it here, but we're going to use protected least significant difference. That is, we're only going to look at this output if the overall f-test is significant. That's protected. It's actually Fisher's protected least square significant difference test. All right. And instead of just running this, because we're actually interested in three dependent variables: spherical equivalent, peripheral, spherical equivalent, and relative. So we're going to say paste. And this reminds us of the that's the wrong button. Reminds us that we can copy our syntax. So this is what I just copied. And I have the same thing up here. And then I just copy, or I have this, I copy this, paste, and paste. And I replace the word spherical equivalent with peripheral spherical equivalent, relative peripheral equivalence, and peripheral refraction. And we can run them all. You don't have to have everything overlapped. You just have to touch each one and press run. And then it just ran all three. So here's the log. We have spherical equivalence. We have peripheral spherical equivalence. We have relative peripheral refraction. And so let's see what our output looks like. We'll just take one of them. First thing we see here is, well, first you can check make sure your code was right, but then you look at the model dimensions. There is an intercept, and it takes one parameter. There are 8 levels of years, -3 to plus, or -4 to +3. When you add the 0 is 8. And that's 7 degrees of freedom, or 7 parameters that have to be estimated. Compound symmetry has 2. It's got the diagonal and the off-diagonal. And that's for a total of 17 levels, 10 parameters to be estimated. The next thing up is information criteria. This is a measure of fit. If we were going to compare the compound symmetry with autoregression, this is where we would determine which is the best fit. So we'd run the analysis again with autoregression, and we would see which of these the number was smaller. And you pick the smaller number. Now, you want to keep the model as simple as you can, so it has to be substantially smaller, and there's no real guideline to that as to whether or not you use it. Down here next we have our basic analysis of variance source table. We see that for init years with 7 degrees of freedom, we had an F of 29 and a P of 0. well, it's not 0, a p less than 0.0001. And it's a small p-value. We would say that this is statistically significant. Now, it's important to know what that means. The p-value is an index of fit on how well the model fits the data. And in this case, the model is the null hypothesis. The null hypothesis is this kind of artificial straw man that says all init years are exactly the same. In reality, that doesn't happen. You could run enough subjects so that there would always be significance. But in this case, when we're testing whether this index, basically our representative of the data is this f-score. So this represents a summary statistic, and if the null hypothesis were true, then this is the probability of finding an f of 29.27, assuming given the null hypothesis is true. If the null hypothesis were true and we got the exact number for the null hypothesis, this value would be 1. But it is 29 times bigger than that, so the p is really small. So these data are not compatible with a null hypothesis. So we reject the null hypothesis. It's important to keep in mind that it doesn't say anything about how big the differences are. And we will address that with effect size and confidence intervals. The next thing in the estimate of the fixed effects is this regression model. It's an intercept plus a parameter for each year up until the positive 3 years, which serves as the reference point. So for 4 years prior to onset, the average peripheral refraction, relative peripheral refraction, is minus 4.4 diopters less than the plus 3. We have next our estimate of covariance. Now, this is an important number, this estimate of CS diagonal offset. That number, the square root of that number, is the pooled standard deviation of all the data. So this is a useful number when we go to compute effect size and confidence intervals. Next we come down to estimates. Now it's important to realize that if you did descriptive analysis on this relative peripheral refraction, if you took the mean, just the mean from the raw data of all these numbers would not be the same. These numbers come from this regression model. So for year 0, it's 0.2 minus 0.41 or minus 2.05. And then for year 0, it's 0.1852 plus 0.20, so 0.21, let's say, 21 and 19 is 0.40. And we come down here and see that's pretty close to that. So these are the estimates. Do not use these standard errors for computing confidence intervals. We'll get to that later. Pairwise comparisons, we're interested in what's the difference from the year of onset. So this is the year of onset at 0 compared to all the other options, minus 4 to plus 3, without a 0 in there. And the p-values we can see from 4 to minus 1 are all different from the year of onset. But after the year of onset, they're not different until you get to the 3rd year. Okay. That's it. That's the mixed model review.